This conference will now be recorded.
Hello everyone. Last day we have started group 18 and some aspects, some atomic properties trend we have seen, and how xenon compound, xenon it forms different types of fluoro compounds, that also we have seen. Now some more aspects of xenon fluoride compounds, and after that their structures will also be discussed, okay, and related problems. Xenon fluoride. So when it is xenon fluoride, that is the first fluoride that is possible for oxidation state of xenon plus 2. It dissolves unchanged in water or acidic solution. That means if you are dissolving it in water, there will be no chemical change. Even if it is acid, then also there is no change. But if you are keeping it for a very, very long time, then decomposition will start. And decomposition will be faster if you are also adding some alkali. Now without alkali, XeF2 when reacting with water, it is forming xenon, HF and O2. Okay, so that is why HF, that is the byproduct. Now as this is acid, so when you are adding alkali, obviously this acid will be consumed. That means equilibrium can be shifted easily from left hand side to right hand side. So that is the reason. Without alkali also reaction will take place, but if you want the reaction to be fast, then you have to add alkali, because one of the byproduct is acid, and if you are adding alkali, then it will be consumed easily, so equilibrium will be shifted and reaction will be fast. Next fluoride is xenon F4. How it reacts with water? It reacts with water, but you can control the reaction products. How you can control it? By controlling the temperature. So when the temperature is so low, it is minus 80 degrees centigrade, then the hydrolysis is not complete. So the first example, that is complete hydrolysis, but the second one is not complete hydrolysis. So when it is partial hydrolysis, product is oxyfluoride. That means both oxygen, fluorine, both are present. But if it is complete hydrolysis, now the products are xenon itself, xenon oxide, HF and oxygen. And when it is partial, now the products are different. HF is also produced, but now instead of xenon, xenon oxide and oxygen, we are getting only xenon oxyfluoride. So you can control the reaction product by controlling temperature. After that, xenon F6. Now the oxidation state of xenon, it is +6. That means it is highly electron deficient. So that is the reason this fluoride compared to XeF2 and XeF4, now the reaction with water will be very vigorous in nature, and product is xenon trioxide. But here also you can get partial hydrolysis. This is complete hydrolysis. But partial hydrolysis of same fluoride XeF6, now it is giving oxyfluoride XeOF4 and XeO2F2. So see, here also we have seen partial hydrolysis and product is XeOF2, but now the product is XeOF4 when it is XeF6 and one water molecule. But if it is 1:2 ratio of moles, now it is different product. Now it is XeO2F2, and when it is 1:3, now the product is xenon O3, that is oxide. So now it is containing only oxygen, there is no fluorine. But when it is partial, there is both presence of oxygen as well as fluorine. So that is partial hydrolysis product. So any doubt in these four different types of reactions? So these are the hydrolysis product of different types of xenon fluoride: XeF2, XeF4, XeF6. Fluoride compounds of xenon can also form complex. For example, XeF2 can react with fluoride ion acceptor to form cationic species. That means here we have used PF5, and PF5 is fluoride ion acceptor. That means it will accept fluoride F- ion And if one of the F minus ion is lost, now it will be Xef plus. And as PF5 is accepting one F minus, now it will be PF6 minus. So overall, this molecule is neutral, but the cationic part, this is ionic. Cationic part is xenon F because it has lost F minus, and the anionic part is PF6 minus because it has gained F minus. Okay. Similarly, another example, SbF5. Now this is also fluoride ion acceptor, and as it is accepting F minus from SbF4, so now it will be converted to Xef3 plus. Just previous example, similar type of reaction. And SbF6 minus. So plus and minus overall neutral, but this is the cationic part, this is the anionic part. So in this way, in this complex formation, what we are seeing, it is accepting fluoride ion, but reverse is also possible. So what I mean by reverse, now fluoride ion, it can also react with fluoride ion donor. So here it is fluoride ion acceptor, that is the other reagent that you are using. They are fluoride ion acceptor. That means xenon fluoride is giving F minus, but now fluoride, xenon fluoride is accepting F minus. Try to understand the difference. Now we are using the reagents MF, where M is sodium, potassium, rubidium, cesium. All are from S block metals, that is group 1 metals. Okay. So these group 1 metals, they can donate F minus, and after accepting one F minus, now it will be Xef7 minus. So now the cationic species is formed by M plus because this F is already lost, and anionic part is formed by xenon. Okay, so this is also example of complex formation, but in the previous box, it is there is a second reaction partner. They are fluoride ion acceptor, that is PF5 SbF5, but now it is metal F. And also if it is 1:1, you are getting this type of complex. If it is 1:2, now Xef6, it is accepting 2F minus. So now it is Xef8 2 minus and M plus, and total, that is this moiety, it is formed total 2 moles. Okay, so in this way complex formation for xenon fluoride is possible, both with fluoride ion acceptor molecules as well as fluoride ion donor molecules. Okay. Xenate ion and Perxenate ion. So there are two specific type of ions formed by xenon, and these are the names. We will see them one by one. How we are getting these ions, that we will see first. So we are getting it starting from xenon trioxide. When you are dissolving this trioxide in water, first there is formation of xenic acid. Now xenic acid is having formula this H2XeO4. Now this acid, it is not very stable. So immediately after formation, there will be dissociation of this in H plus and HXeO4 minus. Okay. So this is the dissociation product. So when XeO3 forms xenate ions, this is xenate ion. Because it is carrying negative charge, so it is ion, xenate ion. So XeO3, it is forming xenate ion after reaction with water. And if it is alkaline medium, then it will be better, because see here after dissociation H plus is produced. So if you are using some base will capture this H plus easily. As a result, equilibrium will be shifted to right hand side, and formation of xenate ion will be, the process will be more facile. But this xenate ion also, it is not very stable. There is a disproportionation reaction going on, and ultimately xenate is converted to Perxenate. See, when it is xenate ion, it is HXeO4 single negative charge. But when it is Perxenate, now it is XeO6 4 negative charge. Okay. Now here we have seen after hydrolysis with water how this ion is forming. But directly you can also treat XeO3 with NaOH, and in this case you are getting directly this ion, that is NaHXeO4. NaHXeO4, it is nothing but Xenate. Why? Because just simply remove the sodium, what you will be getting? HXeO4 minus. Na plus, this is minus. Okay. Now this moiety, if you further add more extra NaOH, now there is formation of Na4XeO6, which is nothing but XeO6 4 minus. Just remove all the 4 Na plus. What you will be left with? Now you will be having only XeO6 4 minus. Okay. Now we will see what is the oxidation state of xenon in these two ions. So when it is Xenate ion, suppose it is oxidation state having X. So HX, for hydrogen we will consider 1, then X. For 4 oxygen it is 4 into minus 2, overall charge minus 1. So what is the value of X? X will be minus 1 plus 8 minus 1. That means 8 minus 2, so it is plus 6. So here oxidation state is plus 6. And when it is Perxenate, now the oxidation state is plus 8. Why? Because 6 oxygen, that means total negative charge from oxygen is 6 into minus 2, minus 12. Total positive charge 8. So plus 8, minus 12, extra negative charge 4 minus. Okay. So from plus 6, now it is converted to 0 oxidation state and plus 8 oxidation state. That means it is disproportionation, because when simultaneously in the same equation, same species is undergoing oxidation reduction, both in the same simultaneously, then it is disproportionation. So from plus 6 to 0 means it is gaining electron, and from plus 6 to plus 8 it means it is losing electron. That means oxidation. So that is why it is disproportionation. So you are getting Perxenate from the disproportionation reaction of Xenate. Okay. When barium hydroxide is used as the alkali, suppose you have not used sodium hydroxide, instead you have used barium hydroxide. So what you will be getting? Now obviously instead of sodium Perxenate, there will be formation of barium Perxenate. Okay. Now Perxenate ion is XeO6 4 negative charge. Now to balance this 4 negative charge, you need total 4 sodium, because sodium cannot have more than plus 1 oxidation state. But when it is barium, which is from group 2, and its oxidation state is plus 2. So per barium you have already Ba2 plus charge. So that is why now to balance 4 negative charge, 2 barium enough. 4 sodium, in case of sodium 4, but now it is only 2. So when it is barium Perxenate, it can be crystallized from the resulting solution, and that is already experimented. So is it clear what is Xenate ion, what is Perxenate ion, and what are their oxidation state, how to find it out? Any part I have to repeat? Now this Perxenate ion, that is XeO6 4 minus, it is very strong oxidizing agent. Now when we say strong oxidizing agent, there are some reagent which easily come in our mind, right? For example, KMnO4, then potassium potassium dichromate. Okay, but this species, that is Perxenate, it is so oxidizing that even it can oxidize, that is Mn2 plus to MnO4 minus. So normally most of the time what we see, that MnO4 minus, that is KMnO4, nothing but KMnO4, where oxidation state of manganese is plus 7. And most of the time you see that it is so oxidizing, it can accept electron and it converts to Mn2 plus. But this reagent, XeO6 4 minus, it is so oxidizing that it can even do the reverse reaction. Now it is accepting electron from Mn and it is oxidizing manganese from +2 state to +7 state. So now you can understand how that is high the oxidizing power is. It is more than even K-. Okay. It can also oxidize silver 1 to silver 3. So we are habituated to see class 1 oxidation state for silver. That is AgCl, then Ag2O, AgBr. But Ag3, that is very unusual. And copper 3, that is also very unusual. Mostly what we see, copper 2 plus and +1, right? But it is so oxidizing, it can even do this type of conversion. Okay. Then barium perxenate solution, which we have already discussed in the previous work, that barium perxenate can be crystallized from resulting solution. So this solution can be used for the synthesis of xenon tetroxide, XeO4. How? If you have taken barium perxenate and you are adding sulfuric acid, now barium is removed and it is forming barium sulfate. It will be precipitated if it is aqueous medium because it is insoluble, and XeO4, this is gaseous in nature, it will be formed. And this compound is actually very prone to explosion. It is not at all stable. So from the temperature you will be getting the idea how unstable it is. You can get that is, you can keep it as stable only if the temperature is below -35.9, that is, it is almost -36. So if the temperature is below this, see how low temperature, then only you can keep it as stable. But if it is greater than this, that is, if temperature is suppose -34, -30, that is greater than this, then there will be explosion because it will decompose. And look at the delage value. It is highly exothermic reaction, -643 kilojoule per mole. This is a very high value. So that is why it will be there will be explosion and it will form ultimately xenon and O2. And why this is so unstable? Because here oxidation state is +8, which is really the maximum oxidation state that is possible, right? Because here for noble gas, what we know, outermost electronic configuration NH2 NP6, that means total 8 valence electron, but +8 oxidation means you have removed all the electrons. All the electrons are involved. So it is really a very unstable state for xenon, and that is why it is stable only when the temperature is below -36. Most metal perxenate are stable, but silver perxenate is not stable. It decomposes violently. So perxenate, you can that is, if you want to get it, we have to make the metal perxenate. For example, sodium perxenate, Na4XeO6, or barium perxenate, that is Ba2XeO6. So in all this metal form, that is salt form, it is more or less stable. Okay. Now some questions we'll see. 6. Xenate ion, this is xenate ion, undergoes disproportionation, that we have already seen in the last slide. And after disproportionation in alkaline medium, here HO- is written, actually it is NaOH. It is converted to perxenate, XeO6 4- for oxidation state is +8, and xenon, and this is +6. So from +6 to +8 and 0, this is disproportionation. And so you are getting these species after reaction with alkali. So the question is the shape of xenate ion and perxenate ions that you have to find. Here we have options. That is the first option, that will be, it is respectively, that means first one that will be for xenate and the second one that will be for perxenate. Okay. Now if you solve any one of these ion, that is xenate, because see, for xenate all the 4 options are different. Sorry, these 2 are same. But if you are finding xenate among these pyramidal or seesaw, then the second one you don't have to solve. You can easily understand which option will be correct. Now we will solve it. Xenate ion, this is HXeO4 minus. Okay, but actually the bonding is that one of this hydrogen, actually it is attached with oxygen, that is xenon OH, and there are 3 oxygen left, and these 3 oxygen, one oxygen will be carrying this negative charge, and other 2 oxygen there will be double bond. Okay, so this is the structure, but we have to find out the shape. It is not simply you draw the structure, you will get the answer. No, that is not possible. So what we will do, we will follow VSEPR, because when we know what is the hybridization, then only we can understand the shape. And to find out the hybridization, we will use this formula: N equal to half total number of valence electron plus number of monovalent atoms plus minus C. That means if it is carrying positive charge, you have to subtract that charge. If it is carrying negative charge, then you have to add. Now monovalent atoms attached, it means you have to consider only the bonds which is single bond. Okay, now this N value, when it is 2, then the corresponding hybridization, it will be sp, that means 2 coordination. If it is 3, it is sp2. If it is 4, sp3. If it is 5, it is sp3d. If it is 6, sp3d2. So in this way we can understand the hybridization, and once you know the hybridization, then the shape we can easily understand. So here valence electron for the central atom, that is xenon, it is 8, NH26, 2 plus 6, it is you have to consider total 8. Here we have single negative charge. Now when you will consider the negative charge, suppose I am not considering M right now, first I am considering the charge. So if it is that is charge you are considering, and there is single negative charge, so it will be +1. Okay, and if you are doing so, in this case, though from the structure that I have drawn here, it seems that 2 monovalent atoms attached, but as you have considered the negative charge, monovalent atoms you have to consider only 1, and it is having value 10 by 2, that is 5. That means sp3d. But suppose if you can also do the calculation in another way. Suppose you are not considering the charge. In that case, that is, if you are considering these 2 bonds as monovalent atoms attached, then you cannot consider the charge. So any of one of these method you can follow, that is up to you, but I will prefer the previous one. Why it is so? Because here, as you can see, directly charge is there, so it will be easier for us to directly add the charge. But in that case, you cannot consider the bond, that is this bond, you at that condition you have to consider it as double bond, you cannot consider it as single. Okay, so there is only one single bond present. But when we are not considering the charge, now the calculation will be 8 plus 2 monovalent atoms attached, that is both these bonds we are considering, and right now charge is not considered. So now it is also same, that is sp3d. So if it is sp3d, that means it will have trigonal bipyramidal structure. Now trigonal bipyramidal structure means xenon. Remember, double bonds are always placed in the equatorial position. So that is why I am writing both the double bond oxygen in equatorial position, axial position HO minus, another axial position O minus. And one coordination site is still there, so there will be lone pair. But it is asking what is the shape. So without lone pair, if we focus on the shape, it is like this, as if xenon is attached to 4 element, like in this way. So if this is the shape like this, it is called seesaw. So without lone pair, the side here the shape is seesaw. So this is present only in option C. So even without considering the shape of Perxenate, you can choose this option as the correct option. Okay, but we will also see how you can do that is similar way, following the similar way, how we can find out the shape of Perxenate. So Perxenate is XeO6 4 negative charge. Okay, so in this case also, even you don't have to draw the structure, just find out n value. You can, whenever there is oxygen, you can directly consider these as if attached by double bond. Okay, so 8, there is no monovalent atoms attached, all are double bonded oxygen, but charge we will consider 4. So it is 12 by 2, that means 6 octahedral. Okay, this one. So if it is octahedral, the structure, and it has to be octahedral because see in the second one it is octahedral. Xenon, 6 oxygen. Among them, 4 oxygen are carrying negative charge. So seeing this structure, if you think that monovalent atoms attached, but no, as you have considered this 4 negative charge, so you have to consider as if there is double. Okay, so that is why simply follow from this of that as if all the oxygens are attached to xenon as double bond, and you just consider monovalent atoms attached, it is 0, and add all the 4 negative charge because it is negative charge, so you have to add it. Okay, so see, this is the octahedral shape, and all the oxygen, so there is no question of lone pair. Fine, that is why correct option will be option C, seesaw and octahedral. Seesaw is for Xenate, octahedral is for Perxenate. So is there any doubt? Should I repeat?
No, ma'am.
The next question is assertion reason type of question. So in assertion reason type of question, normally there are 4 statements there, but I have not written that because it is known to everyone. Assertion is saying that sodium percent, this is the formula, reacts with sodium fluoride in acidic medium and it gives XeO3 and fluoride. These are the reaction products. And the reason statement is Perxenate ion, that is this ion is already present in this molecule. Just remove all the 4 sodium plus, you can get that. This is stronger oxidant than F2. Now we know that F2 is very strong oxidizing agent, that we know. And after accepting electron, it is converted to F minus, right? Because it is accepting electron. And if XeO6 4 minus, if it is even stronger than F2, then what will happen? XeO6 minus, it can accept electron from F minus and it can convert it to F2 because now the oxidation state is 0. So in presence of XeO6 4 minus, if F minus is losing electron and converted to F2 diatomic fluorine, we can say obviously XeO6 4 minus is stronger. And look at the assertion statement. In assertion statement is saying it is reacting with NaF. NaF means what? F minus. And it is reacting with F minus, it is producing F2. That means what? It is converting F minus to F2. And that is possible only when XeO6 4 minus is stronger oxidant than. So I am trying to say both the statement individually correct and reason is also the correct statement. That is correct explanation for assertion. Now look at this reaction. XeO6 4 minus, though I have written this equation here, but you don't have to write this equation if you are lacking in time, because just look at the assertion statement. It is simply from this it is very clear that NaF, that is converted to F. Okay, that means it is conversion of F minus to F2. And if you know the reaction, then it is fine. XeO6 4 minus, this is the Perxenate ion. You can also write the sodium, all the sodium ions. It is reacting with F minus. This is nothing but 2NF in presence of acidic medium. It is now converted to +6 state. That means here xenon is reduced from +8 to +6, and F minus is oxidized to 0 from -1. So this is oxidation and this is reduction. And it is possible because XeO6 4 minus is more stronger oxidation than F. Oxidation number of xenon decreasing from +8 to +6, but for fluorine it is increasing from -1 to 0. That means it is loss of electron. Okay. Therefore, this is reduced and F minus oxidized. So A is true, R is also true. A means assertion, R is reason, and reason is correct explanation. Okay, correct explanation for assertion. So I hope the second question is also clear. Under ambient condition, the total number of gases released as products. That means the products that you are getting, how many different numbers of gases are there in the final step of the reaction, and the scheme is given. So it is not single step, there are several steps. First, you have started from xenon F6, and after complete hydrolysis, because two types of hydrolysis possible, remember the first slide or today's class, partial hydrolysis, complete hydrolysis. If it is complete hydrolysis, there is production of P and other product. Next, you are using some alkaline medium, there is formation of Q, and this Q now show disproportionation reaction, and this is also under the same medium, and now you are getting some products. Remember, in the slide where I have discussed Xenate ion and Perxenate ion, there we have seen that Perxenate is generated from Xenate by disproportionation in presence of NaOH. So this is actually the same reaction. If you look at that, check that slide again, you will get the answer. And this P, that is the first product, that is actually xenon trioxide. And xenon trioxide, this in presence of alkaline medium, first it produces Xenate ion. So this is Xenate ion, HXeO4 minus, and this Xenate ion, which is basically Q, this is Q. Now this Q, this is P, is reacting with further, this is the third step, this is number 1, number 2, number 3. And now this Q is reacting with some more HO minus, and there is disproportionation because from +6 now it is converted to +8 and 0. So with respect to +6 to +8, it is loss of electron, and this is gain of electron. So that is why it is disproportionation, because disproportionation means, as it is mentioned here, both oxidation reduction going on simultaneously. Okay. Now the question is asking under ambient condition, the total number of gases released, okay, as products in the final step. Now in the final step, what you have xenon, which is the noble gas itself, and you also have O2, which is also gaseous. Now this is liquid, and this is also in solution phase, because it will remain in the sodium salt form, and salt cannot be gaseous, right? So how many gases you are getting? Total 2 gases. Okay. So correct option will be option C. Next we have a question, but here we do not have any options. We just have to answer it. Why xenon F6 cannot be stored in glass or silica vessel? Okay. Normally in laboratory, whenever we do any chemical reaction, it is mostly the glass vessels or silica vessels that are used. And glass is nothing but there is presence of silica. But for XeF6, this you cannot do. And what is the reason behind it? That is the question. So see how XeF6 is reacting with silica. In the first step, it is forming xenon oxyfluoride XeOF4. But this is not end of the reaction. It is also forming, that is further reacting with silica, and it is now forming xenon O2F2. And this xenon O2F2, number 1, number 2. Now this is the static material. It is again reacting with another mole of SiO2 and it is forming finally xenon O3. So if you add all this reaction, that is the final product is SiF4 XeO3. SiF4 it's okay, stable compound, but XeO3 it is explosive. That means if you are trying to keep it in glass or silica, there will be explosion because of the formation of XeO3, and that is the reason you cannot store it. Now normally silica is very inert type of nature, and that is why can be used very easily. There is no problem. But for compounds like xenon F6, the problem will arise because this compound, it is not very stable because their oxidation state is +6. Okay, just compare with XeF2, XeF4. They are also fluoride. This is also fluoride, but try to understand the difference. Their oxidation state +2, this is +4. So as oxidation number is increasing, its stability is also decreasing. Okay, because +6 means what? You have to remove all the 6 electrons from valence sheet. Then you can have +6. So more electron you are removing. That means what? More ionization energy you have to provide. You have to provide total 6 ionization energy. But if you are forming +2 state, you have to just provide 2 ionization, which is relatively easy process, right? So that is why XeF6 it is so even you can store these two, but not XeF6. This is the reason. Any doubt in these two problems?
No.
And here remember the first problem is integer type of problem. There is specific category because you are getting some numbers. Next topic is structure and hybridization of xenon compound. Now some idea we have already seen in the previous class also. We have seen how applying this formula, that is half valence electron, number of monovalent atoms attached ±c, how we can get the hybridization, that we already know. Okay, so here the first compound we have is XeF2. It is linear. Okay, XeF2 sp3d hybridization. Now sp3d hybridization means here n value that will be 5. XeF4 sp3d2, that means total coordination 6, so n value is 6. sp3d3. Now see, it is very easy to understand. If you are thinking that how you will remember it, sp3d, that means 1s, 3p, 1d. So hybridization is occurring by taking 1s orbital, 3p orbital, 1d orbital. So after hybridization, you will be getting total 5 sp3. And if you are getting total 5 sp3d orbital, obviously coordination number will be 5 because the central the central element, that is xenon, it will use its 5 sp3d hybrid orbital for bond formation with fluorine. That means coordination number is 5. Similarly, for the second one, 1s orbital, 3p orbital, and 2d. That means 1 plus 3 plus 2. What is the value? It is 6. So in this way, you can easily understand what will be the n value. It is 7, and we will also see this one XeOF2. Okay, this is also sp3d, that means again 5. This is also 6. This is 4. Okay. Now see here, shape and structure that are mentioned, that is actually the shape without lone pair. But if you consider the lone pair, then whenever it is 5, it will be TBP, trigonal bipyramidal. Whenever it is 6, it is octahedral. When it is 7, it is PBP, pentagonal bipyramidal, just like TBP. TBP is trigonal bipyramidal. That is, you have a triangle, and above the triangle, below the triangle, you have two pyramids. That is why it is trigonal bipyramid. When it is PBP, there will be a pentagon. There will be above the plane, there will be pyramid. Below the plane, there will be another pyramid. That is why it is pentagonal bipyramid. When it is 5, again it is TBP. Though it is T-shaped, because without lone pair it will be T-shaped. Then 6, again octahedral. This is tetrahedral, sp3. Now for XeF2, how we will find out the n value? N will be half of xenon, monovalent atom, valence electron for xenon 8. Number of monovalence atoms attached to 2 fluorine attached, and there is no charge. So 8 plus 2, it is 10 by 2, that means 5. So when it is 5, it will be sp3d hybridization. And sp3d hybridization means TBP. So see, this is trigonal bipyramidal. You have triangle, above the triangle there is a pyramid, then another pyramid. But if you just omit the lone pair, suppose without lone pair, if you look at the structure, now it is simply like this without lone pair. So now we will call it linear. So that is why here it is written linear. Similarly, for the second one, here we have the next molecule, which is XeF4. Now for XeF4, again you can use this formula, N equal to half. For xenon it is 8. 4 fluorine, all are monovalent, no charge, neutral molecule. Sorry. So it is 6. That means it is sp3d2, and sp3d2 means 6 coordination, that is octahedral. So when it is octahedral, actual position there will be always lone pair. It is octahedral, 6 coordination, but you have only 4 fluorine. So rest of the 2 position there will be 2 lone pair. So without lone pair, what is the shape? It is simply focus on this part, it is square. But if you are considering the shape, now it is octet. Another way also you can find out the hybridization. For xenon, this is the ground state configuration, NH2, NP6. And when it is excited state, 2 pairs broken and they are shifted to d orbital. Now you have total 4 unpaired electron. Now 4 unpaired electron, it will form bond with 4 fluorine. And these two will be considered as lone pair. Okay, so see, one is 3p 2d. This is sp3d2 hybridization. So any of the method you can follow by applying this formula also you can do, or you can write the electronic configuration in excited state and then try to find out how many lone pairs will be there, what will be the hybridization. Okay. So here square planar is the shape, but actually geometry is octahedral. So in these 2 compounds, that is XeF2, XeF4, is there any doubt? Next we'll go to some other xenon compounds because we are discussing structure and hybridization of xenon compounds. So here we have finished XeF2, XeF4. Some more compounds we will see. Next slide, now we have xenon F6. So half 8 plus 6 plus 0, 14 by 2, 7. Now when it is 7, look at the previously. It is sp3 d3 hybridization, it should be PBP, pentagonal bipyramid, and you have total F6. That means if you are following this PBP geometry, it will be like this. Draw a pentagon, and there are total 6 fluorine, but in the pentagon maximum you can place 5. So from this theoretical concept, this position there should be a lone pair. So this is the ideal structure that we are getting by following the formula that we have done until now. But experimentally it is observed this is not the correct structure. Okay, so this is actually exception. And what is the exception? Here theoretically we should get PBP, but ultimately, that is experimentally, it is obtained as distorted octahedron. Now what is the difference between octahedron and distorted octahedron? If it is octahedron, it is very simple. There will be a that is central metal, any element, suppose xenon, and total 6 coordination site will be there. There is no question of 7 coordinations. But when it is distorted octahedral, now what is happening? See, in distorted octahedral, we have placed all the 6 coordination site, we have placed 6 fluorine. But this lone pair, it is as if it is in between this phase. And which phase? If you join these 3 fluorine, you will be getting a triangular phase. And as if this lone pair, it is protruding from this phase. So it is something unusual. This type of structure we do not see, but it is the experimental observation. So though from theoretical formula that we use, we are getting PBP, but actually it is not the structure. And remember, this is the exception. And be very careful about this molecule, because only for Xef6 this type of observation is found. So here the lone pair, it is not in any particular coordination site. It is in the middle of this phase containing 3 fluorine. Okay, so that is why it is distorted octahedral, because the structure is not symmetric. Because where the lone pair, that is without lone pair, if you look at the structure, it is completely symmetric structure. Okay, but when you are placing the lone pair, now it is distorted. Then the next molecule is XeO F4, square pyramidal. But how you are getting this? Half, 8, total 4 monovalent atoms. Because this bond we will not consider, it is double bond, and overall the molecule is neutral. So what value you are getting? 6. That means it is sp3d2, and sp3d2 means it should be octahedral. So this is octahedral, but you have total 5 atoms, 1 oxygen, 4 fluorine. So the 6th position there must be a lone pair. So if you consider the lone pair, it is octahedral. But if you are not considering the octahedral, then the shape is simply like this. So it is square pyramid. And the next one is xenon oxide. XeO3. For XeO3, half, then 8, there is no monovalent atoms and no charge. So you will be getting 4. 4 means sp3, and sp3 means tetrahedral geometry. Tetrahedral means 4 coordination site, but you have only 3 oxygen. So 1 coordination site there will be lone pair. So if you consider the lone pair, the structure is tetrahedral. But without lone pair, the structure is simply like this. And it is called pyramidal. So there is only a pyramid. Okay, any doubt?
No, ma'am.
Here another way also, sorry, not another way, another molecule we will see. XeO2 F2. Okay, so XeO2 F2, first I will apply this formula. 8. Number of monovalent atoms only 2. Oxygen we will not consider, and there is no charge. 8 plus 2, 10. 10 by 2, 5. That means it is sp3d. sp3d means TBP. Now when it is TBP, trigonal bipyramid. This is the trigonal, and two axial position there will be double bond. Okay, and see, sometimes actually the structure should be like this, because double bonds are mostly placed in equatorial position. But even if you do it differently, actually result you will get the same, because when you are placing, and remember lone pair will be always placed in equatorial position, not axial position. Now without lone pair the shape is simply like this, and that is called seesaw. Okay, so with lone pair it is TBP, without lone pair it is seesaw. Now here electronic configuration is also written, so another way also you can find it out. When it is xenon, it is NH2 NP6, that is 5s2 5p6. This is the ground state configuration. But when it is excited state, okay, how many sigma bonds are there? 2 sigma bonds with fluorine, 2 sigma bonds with oxygen. That means 4 sigma bonds required. Now for 4 sigma bonds, we have to break. See, we have to break 3 pair. Why? Because here we have 4 sigma bond, but 2 pi bond also. That means you need total 6 electron. And if you want to get 6 electron, you have to break all this pair. Now see, there are total 6 unpaired electrons. This is S, this is P, and this is 5D. Now, when it is pi bond, always remember the orbitals that are not used, that electrons that are not involved in hybridization, those electrons are actually pi bond. Here, these 2 electron, see, last 2 electron, that will be pi bond, that will be used in pi bond formation, because without this you have sp3d. Now sp3d, when you are doing the hybridization, there will be total 5 sp3d. So now you have total 5 sp3d, and if it is 5 sp3d, 4 sp3d will be used for bond formation with oxygen, and it is sigma bond. These 2 will be used for sigma bond formation with fluorine, and this will contain 2 electron as lone pair, this one. Okay, so these 2 electrons are not part of hybridization, because whenever there is pi bond, they are not part of hybridization, only sigma bonds are part of hybridization. Okay, so by writing the electronic configuration also, you can understand what is the hybridization. So any one of this method can be used. So any doubt in this discussion, that is regarding structure and hybridization of xenon compound? Should I repeat any part? And also you can say regarding all the slides, because this will be the last slide. After that, in the next class, we will discuss about the application of noble gases. So if there is no doubt, we will end the session here. Thank you for listening.